Deep beneath the border of France and Switzerland, in a tunnel 100 meters underground, there is a machine racing tiny pieces of matter around a 27-kilometer ring at a speed so close to the speed of light that the difference almost disappears. Inside it, conditions exist that are found nowhere else in the universe. Places colder than the depths of outer space, sitting right next to flashes hotter than the heart of the sun. It is the largest, most complex machine human beings have ever built. It took thousands of scientists from over 100 countries, decades of work, and roughly $10 billion to create. And its entire purpose is to do one thing: smash invisible particles together so violently that for a fraction of a second, scientists can glimpse what the universe was made of at the very beginning of time. This is the Large Hadron Collider. And today we're going to understand what it actually is, how it works, why on earth anyone would build something so insane, and the genuinely mind-bending things it has shown us. Because by the end, you'll see that this machine isn't just smashing particles. It's a time machine pointed at the birth of everything. Let's start with the basics, because the name sounds intimidating, and the idea is actually beautifully simple. What is a particle accelerator? At its core, it's a machine that takes the tiniest building blocks of matter, speeds them up to incredible velocities, and crashes them into each other. And that's it. The reason this is useful comes down to one strange truth about reality. The only way to find out what something is truly made of is to hit it hard enough to break it open. Imagine you had a sealed watch and no way to open it. One brutal but effective way to learn what's inside would be to smash two watches together at enormous speed and study the gears, springs, and screws that go flying out. Particle physicists do exactly this, but with the fundamental pieces of reality itself. They take particles, accelerate them to nearly the speed of light, collide them head-on, and then study the shower of even smaller, stranger pieces that burst out of the wreckage. Those flying fragments are the clues. From them, scientists reconstruct the hidden machinery of the universe. So why does it have to be so enormous, this 27-kilometer ring? Here's the key idea. The faster you can make a particle go before it crashes, the more energy is in the collision. And the more energy you have, the deeper into the structure of matter you can probe. And the more exotic, massive, never-before-seen particles you can create out of that energy. To get particles moving that fast, you need to give them a very long runway and push them again and again, lap after lap. That's why it's a ring. The particles don't just get one shove, they loop around the circle and get accelerated a little more on every single pass, building up speed over millions of laps until they're moving at very nearly the ultimate speed limit of the universe. A bigger ring means you can reach higher speeds and higher energies. The LHC is so big precisely because it's reaching for energies nothing on Earth had ever touched before. Now, let's actually walk through how it works, step by step, because the engineering is staggering. It begins, almost comically, with a simple bottle of hydrogen gas. Scientists strip the electrons off hydrogen atoms, leaving bare protons. These are the hadrons the collider is named after. Those protons are then fed through a series of smaller accelerators that get them up to speed before being injected into the main 27-kilometer ring. And here's the clever part. The protons are split into two beams that travel in opposite directions in two separate pipes around the same ring, so that later they can be steered into a head-on collision for maximum impact. To keep these beams whipping around a circle instead of flying off in a straight line, the machine uses thousands of incredibly powerful magnets, over 1,000 of them, to bend and focus the beams. And to make those magnets strong enough, they have to be supercooled, which brings us to one of the most astonishing facts about this machine. The Large Hadron Collider is the coldest place in the known universe, colder on average than the empty depths of outer space. To make its magnets work without wasting energy, they're chilled with liquid helium down to about -271 degrees Celsius, just a couple of degrees above absolute zero, the coldest temperature that can physically exist. At that temperature, the magnets become superconducting, meaning electricity flows through them with zero resistance, letting them generate magnetic fields tens of thousands of times stronger than the Earth's. And here's the beautiful contradiction. This same machine, which is colder than space, also creates some of the hottest conditions in the universe. When it smashes heavy particles together, the tiny point of collision can reach temperatures more than 100,000 times hotter than the center of the sun. So you have, within the same ring, the coldest place in the universe sitting right beside flashes hotter than a star. That alone tells you this is no ordinary machine. And the speed. The speed is almost impossible to wrap your head around. At full power, the protons in the LHC travel at 99.9999991% of the speed of light. That is not a typo. They are so close to light speed that the gap is almost meaningless. At that velocity, a proton zips around the entire 27-kilometer ring more than 11,000 times every single second. In the time it takes you to blink, a single proton has lapped that gigantic underground circle tens of thousands of times. And then there are the collisions themselves. When the two beams are finally allowed to cross, the machine produces something on the order of 600 million collisions every second. 600 million. Each one a tiny explosion, each one potentially holding a secret about the universe. The detectors built to watch these collisions are themselves the size of buildings, packed with sensors that can track the path of a particle with almost unimaginable precision, sorting through that flood of data to catch the rare, interesting events hidden inside the chaos. Now, here's a fact that completely flips your intuition. With all this talk of titanic energy, you'd assume each collision is some kind of devastating blast. But on a human scale, the energy in a single proton collision is shockingly tiny, roughly the energy of a flying mosquito, or a needle dropping onto the floor from a few centimeters up. That's it. The genius of the LHC isn't raw power in the way we normally think of it. It's concentration. It takes that mosquito's worth of energy and squeezes it into a space 10 trillion times smaller than the mosquito itself. It's not about how much energy, it's about cramming it into an unimaginably small point. And that incredible concentration of energy in a tiny space is what recreates the extreme conditions that existed at the very dawn of the universe. Conditions that haven't naturally existed since a tiny fraction of a second after the Big Bang. Which finally brings us to the big question. Why? Why build a $10 billion, 27-kilometer, super-cooled monster just to smash invisible specks together? The answer lies in something called the Standard Model. Over the last century, physicists pieced together a kind of master map of reality, a list of all the fundamental particles that everything in existence is built from, and the rules for how they interact. This map is called the Standard Model, and it is one of the most successful theories in all of science, predicting the behavior of the universe with breathtaking accuracy. But for decades, there was a gaping hole in it. The map predicted that one particular particle had to exist, a particle that was responsible for one of the deepest mysteries of all: why anything has mass at all. Why does a proton weigh something? Why isn't everything just weightless energy zipping around at light speed? The theory said there must be an invisible field filling all of space, and as particles move through it, they get slowed down and gain mass, like running through water. And that field had to have a particle attached to it. But for nearly 50 years, nobody had ever seen it. It was the single most important missing piece of our understanding of reality. That missing particle was the Higgs boson, and finding it was one of the main reasons the LHC was built in the first place. The problem was that this particle is fantastically difficult to catch. It doesn't sit still waiting to be found. When it's created in a collision, it exists for the tiniest sliver of time imaginable and then instantly falls apart into other particles, leaving only a faint trace in the wreckage. The only way to find it was to create millions upon millions of collisions and sift through the debris, hunting for the statistical fingerprint it leaves behind. And on July 4, 2012, after decades of theory and years of searching, scientists at CERN made the announcement the entire physics world had been holding its breath for. They had found it. They had detected the Higgs boson, confirming the last great missing piece of the Standard Model. It was a triumph half a century in the making, proof that the invisible field giving mass to everything in the universe was real. Without it, atoms wouldn't hold together, stars would never have formed, and you wouldn't exist. The LHC had reached back to the foundations of reality and confirmed how the universe gets its substance. Now, you may have heard darker things about this machine, and we need to talk about them because the myths got genuinely wild. When the LHC was about to switch on, some people became convinced it was going to destroy the world. The most famous fear was that it would create a black hole that would swallow the Earth. Someone even tried to take CERN to court to stop it. So let's address it head on, because the reality is both reassuring and fascinating. First, the energy in these collisions, as we said, is about that of a flying mosquito, nowhere near enough to create a dangerous black hole. Even in the wildest theories where a microscopic black hole could form, the physics says it would be so unbelievably tiny and unstable that it would evaporate instantly in a fraction of a second, long before it could ever swallow anything. But here is the single most powerful argument for why the LHC is completely safe, and it's beautiful. Nature has been running this exact experiment for billions of years. High-energy particles from space, called cosmic rays, constantly slam into the Earth's atmosphere with energies far greater than anything the LHC can produce. This has been happening to our planet, and to the moon, and to every star for the entire history of the universe, countless times, every single second. And yet, the Earth is still here. The stars are still here. If these collisions were dangerous, the universe would have destroyed itself long ago. The LHC isn't doing anything nature hasn't already done a trillion times over. It's just doing it in a controlled place where we can finally watch. And speaking of the strange and the exotic, the LHC lets scientists study one of the most science fiction-sounding substances in existence: antimatter. Antimatter is real, and it's bizarre. It's like a mirror image version of ordinary matter, and when the two touch, they annihilate each other in a burst of pure energy. One of the deepest mysteries in all of physics is this: when the universe was born, there should have been equal amounts of matter and antimatter, and they should have completely wiped each other out, leaving nothing behind. No stars, no planets, no you. But somehow there was a tiny, tiny imbalance, a little more matter than antimatter, and that leftover scrap of matter is everything that exists today. Everything you've ever seen is made from that cosmic surplus. The LHC and its experiments are working to understand why that imbalance exists, why there is something rather than nothing. It's one of the most profound questions a human being can ask, and this machine is one of the only tools we have to chase the answer. But here's something that surprises almost everyone, and it's maybe the best argument for why this kind of useless research matters. You might be wondering, okay, this is fascinating, but what does smashing particles actually do for me in my normal life? The answer is more than you'd ever guess. The organization that runs the LHC, CERN, is the very place where the World Wide Web was invented. A scientist there needed a better way for researchers around the world to share information, and so he created the system of links and web pages that became the internet as you browse it today. It was given away to the world for free. The single most transformative communication technology in modern history was born as a side project at a particle physics lab. And it doesn't stop there. The technologies developed to detect particles and handle their radiation led directly to advances in medical imaging. The same physics is used in PET scanners, one of the most important tools doctors have for detecting cancer. Beams of particles, accelerated by descendants of this same technology, are now used to treat cancer tumors with incredible precision. The pattern of history is clear. When humans chase pure, fundamental curiosity, when they ask, what is the universe made of, with no immediate practical goal, the discoveries that fall out along the way end up reshaping everyday life in ways no one could have predicted. The frivolous question becomes the foundation of the future. So let's step back and take in the full picture of what this machine really is. It is the coldest place in the universe and home to flashes hotter than the sun. It pushes matter to within a hair's breadth of the speed of light. It recreates conditions that haven't existed since the universe was a newborn. It found the particle that gives the cosmos its mass. It accidentally birthed the modern internet and gave doctors new ways to fight disease. And here is perhaps the most humbling thought of all. After everything the LHC has discovered, scientists estimate that all the ordinary matter we understand, every star, every planet, every atom, everything the Standard Model describes, makes up only about 5% of the universe. The other 95% is dark matter and dark energy, mysterious things we can barely detect and do not understand at all. So the greatest machine ever built, after all its triumphs, has mostly shown us the edges of our own ignorance, how vast the unknown still is. It hasn't closed the book on reality. It's shown us we've only read the first page. And somewhere under that border in Europe, right now, protons are still racing around in the cold and the dark, slamming together 600 million times a second, chasing the rest of the story, the 95% of everything that we still cannot explain.